short lecture on the mechanics of a particle. So just a quick information, I'm going to do a video series on classical mechanics and basically an undergraduate degree in classical mechanics, which will cover classical mechanics. It'll cover various things. It'll also cover Lagrangian mechanics and things like that. But actually, let me tell you what exactly I'm going to cover. Basically, we're going to be following the book by Goldstein. It's called Classical Mechanics. What is it called? It's called Classical Mechanics, the third edition, and I'm going to be following the book by Goldstein. So first we're going to survey elementary particles, then we're going to go through the variational principles and Lagrange's equation, followed by the central force problem. So that is basically about gravity, but it also applies to some degree also to circular orbits of of atoms. Then we're going to talk about the kinematics of rigid body motion, then the rigid body equations of motion, oscillations, and then finally we will wrap it up with the classical mechanics of the special theory of relativity, Hamilton's equation of motion, canonical transformations, Hamilton-Jacobi theory and action variables, classical chaos, canonical perturbation theory, and introduction to Lagrangian and Hamiltonian formations for continuous systems and fields. So that's basically about field theory. So this is going to be basically 13 chapters, and each chapter has about 5 to 10 different lectures, maybe even more. So this is going to be quite a comprehensive video series, and yeah, so let's dive right into it. So first we need to ask the question, what is classical mechanics actually concerned with? So there are different theories in physics. One of them is classical mechanics. Other ones obviously quantum theory, quantum field theory, and also general relativity, special relativity. Of course, special relativity is part of classical mechanics. That comes maybe as a surprise to you, but special relativity is a part of classical mechanics. And yeah, other theories are also string theory and loop quantum gravity. Maybe we will get to them in a future lecture series, but this course is only going to talk about classical mechanics. So basically it is the mechanics of small point particles, so or rigid bodies or fields, like in the last chapter. But the best way to understand what classical mechanics really is about is to actually go and do it. So let us start. Okay, so first of all we're going to talk about the radius vector. So let us say we have a frame of reference like this, and we'll come to the concept of a frame of reference later in more detail. So let us say we have a frame of reference with x, y coordinates and z coordinate, and let us say we have a point particle somewhere in this space, and it moves along a certain trajectory like this, for example. So then the vector from the origin of the frame of reference to this point here would be r, and it is a function of time. So another thing which I wanted to note is that you should have some basic knowledge of calculus. Well, actually not basic knowledge, you should have good knowledge of calculus. And there are several courses online, or maybe you can go through a textbook from your school time. But yeah, so you need to know classical mechanics. So okay, so that out of the way. So we have basically our radius vector, which is basically the position vector of this classical particle in a certain frame of reference. If we choose a different frame of reference, then the radius vector is obviously going to be different, but it is still in the same position, in the sense that in relation to other objects, it will be in the same position, right? So for example, if I look at a box from this side here, and here I have whatever here, let us say you have a cross over here, then from this point of view the cross is to the left of the box, but from this point of view the cross is to the right of the box. So basically this means that depending upon which frame of reference you're in, your description of it is going to be different, but the cross is always next to the box, right? It always is in the same relation to the box. So yeah, so if you have different frames of references, let's draw actually one here. Let us draw another frame of reference. Let's say it looks like this. This is the other frame of reference. Then the position vector is basically going to be this. This is going to be the r dash, for example, as a function of t, right? So it's a different vector, but it describes the same object, and yeah, so that's it. So now what can happen is, obviously the position of this, let us delete actually this frame of reference and this arrow. So if you have this particle moving in space, then you have the position vector, and this position vector is a function of time. So at a certain time instant, the particle is over here, then after some other time instant, it's going to be here. So that's r of t dash, for example, right? And t dash is greater than t, right? I drew now the trajectory like this, but actually you should only have one point, because time is also an axis, right? So let us look another example. Let us say you've got the time axis and you only have one dimension, which is the x-axis x, right? And let us say you have a particle which moves something like this. What does this mean? This means that at this time point the particle is here, at another time point here the particle is here, and then it moves on like that for different slices in the time coordinate, right? So this is basically a particle which moves to the right like this, and then again to the left, right? But actually it's not moving along this line. It's actually moving like this, right and left. It is a projection of this trajectory onto the x-axis, right? It only looks like it's moving in a zigzag curve because we are expanding the time flow in another dimension, right? So this is all I had to say about radius vectors. So remember, the name is basically a radius. The position of a particle is called the radius vector and is usually denoted by r, right? So we've got the radius vector out of the way. So now what we can do is we can define the velocity of a particle. Now the velocity of a particle, let's write the velocity of a particle v is equals to dr as a function of t by dt. So basically it is the first derivative of a function, and actually yes, that's the velocity. Now another thing which you have to differentiate is the speed of a particle. Let's call it s, for example, is not a vector. It is a scalar, and this is basically d and then the length of r as a function of t with respect to dt, right? It's the length of r. Yeah, that gives me the instantaneous speed, because the difference between velocity and speed is velocity is a vector quantity and has also information about the direction, whereas the speed has only information about well, it's the speed of the velocity. It tells me how fast is something moving, irrespective whatever direction it's moving in, right? This is the difference between the velocity and the speed, right? So, and this is the first derivative of r with respect to t. So in particular, this is actually, we call this drx as a function of t with respect to dt, dry as a function of t with respect to dt, and drz as a function of t with respect to dt, right? So it's basically, and drx, dry, and drz, or rx, rv, and rz are just the coordinates of the particle. So r is actually rx, ry, and rz, right? These are the coordinates of the particle, right? And the velocity is the first derivative of each of these coordinates, right? So that is the concept of the radius vector and the velocity. Let us go to another concept, which is called the one of linear momentum. So linear momentum is denoted usually as p, and it is equals to the mass of the particle times the velocity, right? So this is also a vector quantity, and it's just the velocity multiplied by the mass. So yeah, and now we come to a very important law, which is known as Newton's second law, and it's basically that dp, that the derivative of p with respect to dt is equals to the force. This is a definition. It's an axiom, so there's no way to prove it or anything like that. You have to just take it. And but the thing is, these axioms work, and they describe the way nature works. So f is also a vector quantity, right? Now we can come up now we can, so we can also write this as d by dt of m times v is equals to f, right? So this equation is the same as this. So basically what you have to note here is that this m here is usually independent. For our purposes, the mass is independent of time. It's actually a scalar quantity, a constant quantity. For example, the mass of your watch or whatever you have, whatever point particle you're considering, doesn't depend upon time, right? In quantum field theory, this is not true, right? Or in special relativity, well, in special relativity, there's a concept of the invariant mass. We're going to get to that later. But generally, in classical mechanics, we are most of the time concerned with processes where the mass is constant. This doesn't always have to be the case. For example, if you take a rocket, for example, then it's going to lose some mass, and that can also cause it to create momentum in a certain direction, right? That's the whole concept of propulsion. So, but usually the mass is a constant, and then if you know calculus, you know that this can be written as m dv by dt is equals to f, right? I've just taken the differential operator and applied it to the velocity. So this is the Newton's second law in case the mass is constant. So this, if m dot is equals to 0. So usually I also denote m dot as the time derivative of t. So if you have any quantity a dot, is just dA by dt, right? Right. So this gives us another important quantity, namely this quantity over here, and this is known as the acceleration. It is the change of rate of change of the velocity. So we define the acceleration to be equals to the rate of change of the velocity. So this is d by dt of the velocity, and it basically tells you that a particle at constant velocity, the acceleration is 0, right? If it has a constant, doesn't mean that it's not moving, it's just moving at a constant speed. So if it's moving at a constant velocity, then the acceleration is 0, right? But if it is not moving at a constant velocity, then there is some acceleration, and therefore there's also a force. So this brings us to the concept of we'll come to the conservation laws for linear momentum and a particle later. But an important concept is that in classical mechanics we consider reference frames, which I already talked about, and there's a special class of reference frames which are called inertial frames of reference, or a Galilean system. And reference frames generally have the property that there is no acceleration between these frames, right? So we're going to get to that in the next lecture in more detail, but for now what I want you to remember is the concept of the position vector or the radius vector, which is r. Then you should know the velocity, which is basically the first derivative of r with respect to t, the definition of momentum, which is the mass times the velocity, and then Newton's second law. Let's write this here. Second law, right? Newton's second law, which basically says that the momentum, the rate of change of momentum is equal to the force, right? So, so yeah, that's it. That is what I wanted to talk about in this lecture. So please stay tuned for more content like this. We're going to get into more interesting content in classical mechanics, and I hope to see you in the next video. Thank you. Bye.